Okay, so hi everyone. Thanks very much for turning up outside official lecture weeks. So I hope it's worth it. I should say, I know I promised last week 0 equations. I did look at the slides and I couldn't resist putting in just a couple. So I hope you don't kind of feel like resentful that you've actually turned up and then like really showing you an equation after all. So this lecture, we're really going to focus on, I think, one of the big success stories of reinforcement learning, and I hope to persuade you that not only is it an interesting testbed for understanding reinforcement learning, but it also will help you understand really how to make progress in a large set of interesting games, which I call classic games, games that people have played for many, many years and particularly popular. So there's a fair amount of different kind of areas we're going to try and go through. But I really want to focus this lecture on what I consider to be the state of the art. So this is a little bit different to some of the other classes, and really my goal is to show you actually how to put together everything we've seen in the rest of the classes to really achieve state-of-the-art performance. And so what I'll focus on is not maybe the canonical examples of reinforcement learning, but rather what's actually worked, what's worked really well in these classic games, so that you can actually understand, at least to some level, what's been used to reach superhuman performance, for example, in certain games. To do that, I've put in just a little bit of game theory, very minimal, just to help understand what it means to do reinforcement learning in this setting, what it means to even talk about optimal behavior when we have more than one agent involved in the situation. And then we'll focus on minimax search, which is a special case for two-player zero-sum games, which is the main class of game that we're going to consider in this lecture. Then we're going to talk about really how you achieve performance. Now we're going to talk about reinforcement learning by games of self-play, agents that just play themselves again and again and again, and then can go off and beat the top human players in the world. That's our goal. We're going to talk about how to combine these sort of planning ideas, minimax search, high-performance search engines, with reinforcement learning. And finally, we're going to focus, if we have time, not sure if we'll have time for that, on some recent successes in imperfect information games. So this is games where there's hidden state, like card games, like poker. If you want to go out and build a poker bot to beat the world's best players, then here's the recipe. Okay. So, state of the art. So I just want to start by saying, why should we care about this lecture? Why study games at all? I mean, I know a lot of people think, well, games are a little bit, fun or trivial, or why is it an interesting testbed? And I think actually there's a lot of legitimate reasons to really focus on games. First of all, they tend to be the examples that we have, which have the simplest rules but the deepest concepts. I mean, that's how games are designed. They're designed to have rules that you can read in just a paragraph or two. And yet the actual gameplay concepts which get involved require hundreds of years of study for people to become very good at a game like chess or Go. It's evolved over hundreds of years how people play these games. And also I think we can say that games kind of give an IQ test for artificial intelligence research. So if you know how you're doing at a game, you can really benchmark yourself not just against other games by playing in tournaments or computing your rating against other games, but also against humans. So we have these humans who've devoted their lives to playing games, and now we can really match up our computers to a human in a domain where a human has really dedicated decades of their learning time to this, and are really at the pinnacle of what we consider intelligence. So for those reasons, a long time ago, back in the day when AI was sort of coming through, a lot of people focused on games, in particular chess, and chess was called the Drosophila of artificial intelligence. Now Drosophila is Latin for fruit fly, and the reason that chess was called the Drosophila is because just like in genetics, the fruit fly was used as this very easy case study for running lots and lots of experiments, and so you can find hundreds of papers on the fruit fly because it's kind of particularly simple and just became the natural testbed that everyone looked at to understand the deeper concepts. So chess became the Drosophila of AI. And then at a certain point, as we'll see, chess kind of was solved in the sense of achieving superhuman play. People moved on to other games, Go and so forth. And I think also these games, they kind of, although they're very simple, you can think of them as microcosms. So there's some interesting issue that we might care about in the real world, like hidden state. And then you can look at a game that basically simplifies everything else down to very simple rules, but still looks at the situation where you have hidden state. So it gives us a way to understand these in rich but simplified settings. So, that's all very well, but I think, games are fun, so let's have fun today and hope you enjoy finding out about these. That's the real reason, of course. Okay, so This is the one slide I kind of want you to, two slides actually, I want you to really get some understanding of how far we've come with reinforcement learning. So this slide here shows, for all the methods that have been tried in these classic games, all of AI, what has been effective. And so basically what we're looking at is different domains here, so checkers, chess, Othello, backgammon, Scrabble, Go, poker. So that's a selection of the classic games we're going to talk about today, some of the biggest and best known games. And this is the level of play that's been achieved by artificial intelligence systems in those domains. So perfect in checkers means it's literally been solved, the game has been solved, so this checkers program. Chinook can play perfectly against God. Superhuman means it's defeated the world's best human player. And then we've got some things which roughly play at, say, what we might consider grandmaster level now. These Go programs play about 6 Dan now. So that's roughly the level of the best players in Europe. So all of these successes are very powerful, but I guess what we want to know is how far can reinforcement learning get? How much of this has been done with RL? So this slide shows now the same information, but just for methods which are based on reinforcement learning. And what we've looked at now, so now these are reinforcement learning programs to achieve this level of performance in these games. And in each case, I'm looking at the program that was like the first to reach that level of performance, so like the first program to reach superhuman level. And what we see is highlighted in red are the overlaps with the previous slide. So I guess 5 out of 7 of the examples we're looking at were achieved using reinforcement learning. And the 2 which are in black aren't the best examples in their domain, but they've still come an awful long way. So in poker, there is now a superhuman, probably superhuman, reinforcement learning method. In chess, it's perhaps surprisingly, despite being the Drosophila of AI, it seems that RL, it turns out, has got slightly less far on that one, but still reached international master level, as we'll see. So reinforcement learning can achieve really high performance in all of these games, and it's basically the primary mechanism by which success has been achieved in classic games. Okay. So let's talk about game theory. So we want to understand the ingredients that get us here. What's common about these different programs? What were the methods involved in reinforcement learning that we can understand and use, and then go off and use them not just in games but in other domains? So that's really the goal here, is to distill out the essence of what was important in all of these success stories, and then understand those success stories, internalize them, take them away, and be able to do that in any domain you work on. That's the goal. Okay, so let's start by game theory and just understand, what do we even mean by a game? So there's a question which we should be asking ourselves, which is, what does it even mean to make an optimal policy in a game? So in an MDP, all the cases we've looked at so far, single agent domains, it's very clear what optimality means. You just want to maximize your reward in that game. But the optimal policy for the ith player depends on how all the other players play. So that should be clear, that if you're playing rock, paper, scissors, and I'm playing against someone who always plays rock, my strategy, the optimal strategy against someone who always plays rock, is very different to the optimal strategy against someone who always plays paper. They're totally different strategies to win against these games. They're both optimal in some sense, but what do we really mean by the best policy amongst this whole space? So we're going to talk about this superscript we're going to use to represent the player number here. So we're going to have a policy for each player. So the policy is just the familiar policy we've had before, where there's some strategy for picking actions, but each player has their own strategy for picking actions now. And so we're going to talk about something. Let's first of all consider something called the best response. So let's consider the case where I'm in a game and all the other players fix their policies. So if I was playing against fixed opponents, I could ask the question, what's the best way to play against those fixed opponents? So for example, if I was playing rock, paper, scissors, and I was playing against someone who always plays rock, then the best response to that strategy is to always play paper, cover up the rock. So that's the best response to a fixed opponent, someone who always plays in that way. And in multiplayer games, this also applies. You can have the best response to a whole set of different policies, as long as those are fixed. And so this, in some sense, reduces the game to the case we're familiar with. We can just treat all the other players as part of the environment. and then just find the optimal policy against that environment, which includes the way that all the other players are going to play. But this doesn't really help us understand, what the best policy is overall in this domain. We want to understand, well, I don't just care about how to play against this particular opponent, I want the best way to play in this game. So can we come up with a better criterion? And the most famous criterion, in fact it's probably one of the only things I've talked about in this course which is so famous that you can find Hollywood movies about it, like The Beautiful Mind. The Nash equilibrium is basically the main game theory concept for talking about optimality. There are others, I'm going to focus on Nash equilibrium. And a Nash equilibrium is basically a joint policy for all players, so it's a way to pick actions for all players, such that every single player is playing a best response to everyone else. So if you find a Nash equilibrium, it basically says that my policy, if I'm player I, my policy has to be a best response to the policies that everyone else are following. And so that means if we're playing rock, paper, scissors, then my response, the way I play, has to be a best response to my opponent, but the way he plays has to be a best response to me as well. So it can't be the case anymore that I just always play paper, because if I always play paper, he would be able to play scissors and defeat me all the time. So I wouldn't have the best response then to his new strategy, which is to use scissors all the time. So another way to say this is that when we're in a Nash equilibrium, it basically means that no one would choose to deviate from that strategy. So what is that? So in rock, paper, scissors, that means everyone plays 1/3 of the time rock, 1/3 of the time paper, 1/3 of the time scissors. That is the equilibrium strategy. If everyone is playing that strategy, no one would choose to deviate from that strategy. If they did deviate from that strategy, someone else could find a way to play that would exploit that and would be a best response to that strategy. So in the Nash equilibrium, no one would choose to change their strategy. This would be the best thing given everything else that everyone else is playing. So it's something that's like a happy medium amongst all the players. It's like at that point everyone can say, okay, we all think we're playing the best way according to what we're observing of everyone else, according to these strategies that we know about everyone else. Is that clear as a solution concept? Okay, so we're going to use this as like our gold standard for what it means to achieve optimality in games, the Nash equilibrium. If we can find a Nash equilibrium, we'll sort of declare victory and say, that's the best we can do in some sense in this game. It doesn't mean we found the best response to a particular opponent. It just means that we found some strategy which, in some sense, dominates all other strategies against equivalent ways to play, against any other way for the other players to play. Okay, so let's talk about reinforcement learning now. So if we come back to the best response, we can think of the best response as the solution to a single agent reinforcement learning problem. So best response, we can just treat the other players as part of the environment. We take our other player, we push them into the environment. I can imagine I'm playing rock, paper, scissors, where I'm just a single agent in an environment where I happen to be playing some game where there just happens to be some other player who's playing against me, and all I see is their action is what I observe, and I get to pick my action. But we can just treat that other player as part of the environment. We can do all our familiar things that we do when we do reinforcement learning. We can treat that as the environment. We can make an MDP out of rock, paper, scissors or any other game. And now the best response is just the optimal policy for that MDP. So we know how to find best responses. It's basically you create an MDP that represents that game. You fix the opponents. That defines the environment for your MDP, defines the transition dynamics. And you push the opponent into the transition dynamics of your MDP. And then you just solve for that MDP. But the Nash equilibrium is a more powerful solution concept. It tells us something a little bit more profound. It tells us generally about any way to behave amongst all different joint policies amongst all players, which is the best in some sense. And so the way to understand the Nash equilibrium, how can we find this by reinforcement learning? Well, the Nash equilibrium is a fixed point of self-play reinforcement learning. So what I mean by that, so what do I mean by self-play reinforcement learning? I mean, imagine the case where I am in control of all the agents in my game. So I'm controlling player 1 and player 2 in rock, paper, scissors. And I get those agents to play against themselves. So self-play, I'm just trying my own policy against some other policy. I'm controlling this thing. So I'm controlling the policies, I'm learning these policies, and I'm getting them to play against each other by self-play. And so we generate this experience, and we treat that as our experience. And given that source of experience, we want to learn the best response to other players. So if we're in an environment where we're seeing the responses of all the other players, then we're basically learning a policy that's adapting to how all the other players are playing. So we're learning by self-play. We're seeing how the other opponents are playing. We're imagining that the other opponents might play in a certain way. We're adapting. So as my opponent gets better and better and better, I have to adapt and find better and better counter strategies. And then my opponent has to find better and better counter strategies to those. And we keep adapting the policy by self-play, imagining these games, playing against each other. And the point is that if we ever reach a fixed point of this process, which by the way is challenging, it's not clear that all RL methods converge when you try and do this. But if we do find a fixed point, if we do find an optimal policy at any point where all players declare that they found an optimal policy to the behavior that's generated by these other players, that is a Nash equilibrium. So we just have to solve for the RL problem, which is generated by the play of the other players. If we can solve for that RL problem dynamically adapting this thing, and we find a fixed point, we will arrive at a Nash equilibrium. And there's a nice seminal piece of work by Michael Lippmann that I'm not going to talk about, this was in his PhD thesis, where he showed that basically for a large class of standard reinforcement learning algorithms, they do actually converge on the Nash equilibrium, at least in the table lookup case. So it's not impossible to do this. It's, if you use your favorite algorithm, there's a good chance that you really will just converge by self-play to finding this Nash equilibrium, the best way to respond to how your opponent's playing. So it's like an iterative process. We just start playing games against myself. I improve my policy. Each time I improve my policy, I'm changing the way in which experience is generated. I'm changing the RL problem a little bit, and I have to adapt to that until I become better and better and better and better, until if this process actually stops and reaches a fixed point, it's the Nash. Okay? 2 questions, good.
So is the Nash equilibrium, will that be unique if it exists?
Okay, good question. In general, no. For general games, it's not unique. For the class of games we're going to consider, there is a unique Nash equilibrium. So we're going to consider 2-player zero-sum games, which do have a Nash equilibrium in the least imperfect information case. So most of this lecture will talk about the case where there is a unique Nash. But it's not always true. So in a game like poker, for example, there's a whole family of different Nash equilibria. There are many, many different ways to play at Nash. Some of them you might consider better than others because they might generalize to play better against humans, for example. Was that the same question?
No. I was just going to check that I was understanding correctly. So this best response is like what we're doing for our homework. We've incorporated the dealer into our environment, but with Nash equilibrium, we could get to learn the dealer's best policy as well.
Exactly.
Right.
Exactly.
Okay, cool.
Yeah. So this would, if we took the Easy 21 assignment and we now learn the dealer's policy at the same time as we're learning our own policy, and the dealer would be adapting to how our policy is improving, and we'd be adapting to how the dealer's then improving, you would find the best joint policy. And so that would then tell you how to play, not just against that fixed dealer, but potentially against any dealer, because you've learned something which is a much more powerful solution concept that tells you about play in general in this game. Good, thank you. Okay, so we're going to focus on a special class of games. So game theory considers many, many games, but we're going to consider 2-player games with 2 alternating players. So they actually take turns. So, and we're going to call these players arbitrarily. I'm going to call player 1 white and player 2 black. Just think of that as a naming convention. Again, it could be games which don't even have colours. That's fine. And the idea is that white plays, and then black plays, and then white plays, and so forth. It's not simultaneous games for us. And we're also going to consider zero-sum games. So zero-sum game basically means you've got equal and opposite rewards for both players. So if something's good for black, it's bad for white. And if something's good for white, it's bad for black. So it basically means, that every time we're in a situation, there's a very clear definition of what it means to do well in that situation, because both players are fighting in exactly the opposite direction. They're never trying to cooperate to achieve a common goal. And we're going to consider how to find Nash equilibria in these types of games, these two-player zero-sum games. We're going to consider two general methods for achieving this, one of which is like a planning approach. So if you think of the two main families we've considered in this course, we've talked about reinforcement learning, we've talked about planning. So we're going to start off talking about the planning approach, like game tree search. We basically build a big search tree to find the equilibrium solution. And then we're going to talk about self-play reinforcement learning, so methods that just do TD, for example, to find this solution. Okay. And we're going to break this up into perfect and imperfect information games. So perfect information, also known as a Markov game, is fully observed, so you see the entire state of the game. So chess, checkers, Othello, backgammon, Go, these would all be examples of perfect information games. So note that you can still have stochasticity in these games, like in backgammon there's a dice roll, but you see everything, you see the full state of the game, you get a Markov state. In contrast, an imperfect information game is partially observed. So if we think about Scrabble, you don't see the letters that your opponent has on your rack. And in poker, you have a much more serious type of imperfect information where you really don't know what your opponent's cards are, and that really affects how you need to play the game. Okay, and we're going to start with perfect information, spend most of the class on perfect information, and then we'll just spend a little bit of time at the end on these games. Okay, so we'll start with minimax search. So let's get back to our familiar territory of RL and see if we can kind of build up those basic building blocks again in the world of games now. So we want to understand what it means to have a value function now. So a value function we can define in the natural way, which basically means the value function is going to tell us the expected total reward given policies by all players. So we're basically looking at these two-player games. We're going to say there's a policy for black, there's a policy for white, and what we want to know is if black plays in a particular way and white plays in a particular way, how much reward will there be at the end of the game? And we don't need to estimate the value function separately for black and separately for white, because this is zero sum. We know that what's good for black is bad for white, so we can just negate it to get it from the opposite player's point of view. So we just need the one value function, and that tells us, under this particular way of playing for both players, who's going to win, basically. So we can always think of this reward, so that's the return now. Okay, in general there might be games where you have some reward per time step, you might have discounting, you might have all the other things we have in RL, but the normal case in games is there's no reward, no reward, no reward, no reward, no reward, and then at the end of the game someone wins. And then we say that's either a reward of 1 or -1, depending who wins. So that's the standard case we consider. So this then basically tells us, this expectation is who's going to win? What's the probability that black will win this game if both players play in a certain way? And now what we really want to know is, well, what's the best way that both players can play? So if we consider the whole space of different policies for both white and for black, what's the best way to play? And so the minimax value tells us these best possible values. In other words, if white's trying his hardest to maximize the score, and black's trying her hardest to minimize the score, then what will the score be if both of those players are playing in that way? So that's the minimax value function. So this is like a fundamental concept of both game theory and in practice just building any high-performance game system. It's the standard tool is to do try and find this minimax value function. And so we really want to know, what are these V stars? And again, just like usual, if we have the optimal value function, we're pretty much done. In a game in particular, if we have the optimal value function, we know how to play. This tells us, what move we should really take, because we know how to pick a move for black or for white once we have this V star. So a minimax policy then, so if we come back to policies, so minimax policy is any joint policy, any way to play for both players that achieves these minimax values. It achieves the best possible score from white's point of view and the lowest possible score from black's point of view. So both players are striving their hardest to kind of fight against each other and maximize the probability that they'll win the game. And then at the end of that process, that struggle, we want to look at the policies that basically achieve that best possible outcome, and this is the minimax policy. And the value function tells you basically who will win from any state if they're struggling in this way. So another way to say this, under perfect play by both players, if they assume that the other player is playing perfectly against them, then who will win under perfect play? That's basically what this is saying. Now, to answer the question from earlier, in this setting where we have perfect information, 2-player, zero-sum games, there is a unique minimax value function, and the minimax policy that's defined by that minimax value function is always a Nash equilibrium. So it's a very nice special case where just by computing this minimax, you also find the Nash. This is the Nash for these games.
Sorry, can I ask a question?
Yeah.
I'm not clear in my head why it's max and then min rather than min and then max. So yeah, why is it max over pi 1 of min over pi 2 and not min over pi 2 over max over pi 1? What is it?
Let me try and make that clear in the next slides. I think that's going to become clearer. So I think the right way to think of it is it's a nested process. Like whoever's to play first, so if white's to play first, then it would be a max for white first, and then a min for black, and then a max for white, and then a min for black, over all of the actions which are taken over that sequence of steps. That's kind of a shorthand for that, basically. And so we have what we call minimax search, which is the standard way to estimate this minimax values. And so the way to do this is to build your familiar search tree. So if you open any AI textbook, they might not tell you all the slides which came before this, but probably chapter 1 will be this. Right? Chapter 1 will be how do you do minimax search. And the idea is to basically build a search tree where if you're playing tic-tac-toe, noughts and crosses, whatever you want to call it, you start in some position, you consider how white, which in this case is x's, might play, and then you consider all the way that the black, in this case circles, might respond to that. We build the complete search tree, and now we analyze this search tree to figure out what actually is the optimal play by both players, looking at this whole search tree. And so this process of game tree search, you can actually search from this root position to figure out the minimax values. Turns out that this was actually first introduced by Claude Shannon, who's the father of information theory. So in his spare time, he basically introduced the whole of game theory and minimax search in this programming computer for playing chess, which was the first ever chess program, which actually ran on paper because he didn't have a computer to run it on. So he ran it on paper, but it was a valid chess playing program and had a lot of the main concepts in there already back when he developed this. And so if we just run through this very briefly, we can think of this as like some game. So let's consider some game with 2 players, which we'll call max and min. So this is like the, I guess the colours are swapped from what we were talking about, which is a little confusing. The idea is that there's one move for max, then a move for min, then a move for max, and then we basically get some outcome of the game. Like this is the score at the end of the game. And the question is, what's the real score from the top node, from the root node, if everyone plays optimally? If max plays to max at every step and min plays to min. And so this can just be computed in a brute force fashion by doing some kind of search. So imagine we were doing, say, a depth first search. We go all the way down to the leaves, and then we back up this information. And that's the standard approach to minimax search. You do a depth first search. You come down to here. You see a +7 here and a +3 here. So you would say, aha. If max is trying to maximize amongst these values, this node here must have a value of +7, because max gets to choose whether to play here or to play here. And similarly, max gets to maximize amongst these. We see that we've got a value here of -2, which is greater than -4, +9, which is the max of these two, and -4 is the max of these two choices. And then we iterate and we say, okay, well, from min's point of view, we want to then minimize these things. So min gets to choose amongst these actions B1 or B2, and so min gets to choose this action B2, which leads to -2, rather than this +7, which would be great from max's point of view, but a disaster from min's point of view. And similarly, here we've got a choice between -4 and +9, so min chooses to go to the -4. And so now we can see from the root, there's one final decision from max. This is the first decision in the game that gets made, and now we can understand what that first decision should be, because max clearly would prefer to go and choose A1 rather than A2 because it has a higher value of -2. So this is minimax search. It basically gives you a way to compute not just the optimal values, but you can see also now the optimal policy as well. So the minimax policy would be to pick A1 from this root node for max and so forth. So you can see that if we can do this search, we're basically done. We've got optimal play. We've figured out how to do this. And there's only one problem, which is that this search tree in any game of interest is vast. Like it just blows up exponentially with the depth of the game, and typically you can't solve the whole search tree in this way. So in practice, what we do is we, instead of going all the way to the end of the game, we basically truncate the search after a small number of steps, and we use a value function to summarize, to estimate the minimax value from that node onwards. And so if we have this value function, which is in game tree search referred to as an evaluation function or heuristic function, but I think we, in this course, can correctly understand it as a value function. It's something that's trying to estimate the true minimax value. If we have that estimate of the minimax value, so we've got some value function approximator now that's trying to estimate the minimax value. So this could be our familiar function approximators, like a linear function approximator, a linear combination of features, or a neural net. And we've got this value function now, and what we can do is basically, imagine now we've got a game that goes on for 1,000 steps instead of 3 steps. What we can do is we can search down, consider the first 3 actions that we might take, build a search tree over those first 3 actions, and then each of these leaf nodes, after 3 actions, we basically truncate, and we insert our value function here. So this might be the estimator that comes out of our value function approximator. Our neural net says, aha, this position is worth +7, this position is worth +3, and then we back up those estimated values all the way to the root, and we get an improved estimate of how to play the game. And so that is the standard approach to minimax search, which is used in every classic checkers playing program. And what I'm not going to talk about today is how to make this efficient. So, several decades of research went into making efficient minimax search, principally based on a method called alpha-beta search, which is just a way to cut off parts of the search tree which are guaranteed to not be interesting to either player, because we know, for example, that certain parts of this tree will never be visited because of the way that we're maximizing or minimizing. We can cut off large parts of the tree. So that's alpha-beta search, the most efficient minimax search, and there's decades of work on how to extend and improve this. Okay, is that clear to everyone? Good. So what I want to do is just really make this concrete. So I'll give an example using chess, which is like the canonical example where minimax search has been effective, and show how a typical chess program would actually build a value function to use in this minimax search. And so the way that this works is we typically have some position like this. This might be the chess position. And so most chess programs, what they do is they build a binary feature vector, which basically says things like, do I have a white rook in this position? Yes or no. So if I do have a white rook, which I do in this position, that feature will have a value of 1. Do I have a white bishop in this position? Yes. Do I have a white pawn in this position? No, that has a value of 0. Do I have a black rook in this position? 1. Do I have a black bishop here? 0. Do I have a black pawn? 0. So that's kind of your features, just indicators saying, for each of the initial pieces that you have in the game, are these actually present in the position? And then what we have is a value saying how good is it if you have that piece. And this is familiar to every beginner at chess, gets told, well, rook is worth +5, bishop's worth +3, a pawn's worth +1, and then we just reverse that for the opposite sign for the opponent. So if the opponent has a rook, that's -5, -3 for an opposing bishop, -1 for a pawn. And now we can evaluate this position just by taking a dot product of these 2 vectors. Our feature vector here, a binary feature vector here, and our weight vector here, which basically says how good is each of those features. How good is it to have a bishop, or to have a rook, or to have much more complicated features as well? How good is it to have an exposed king? How good is it to have a knight on an outpost? How good is it to have a particular pawn structure? In a typical program we'll have thousands of these features. Each of them gets a value, so maybe not just +1, -1 for pawns, but maybe +0.002 for a particular pawn structure. And then you can just evaluate a position, and this is very, very efficient because you don't need to consider all of the features which are in your feature vector. You just look at the ones, and you just sum up the weights of the things which are actually in your current position. So you just add the 5 for this rook, +3 for this bishop, -5 for this black rook, and that gives you your position. It says, aha, the value of this position is 3. Then if you want to convert this into a probability of winning, we typically just pass it through a logistic function. So I'll kind of assume something like that is done at the end for most of these games now. So you can kind of squash that back down to a probability of winning if you want. Okay, is that clear? Good.
So how about their location? Like, is it not important?
Sure. So you can make this as rich as you want. So, so you normally have the piece value. The piece values are like the primary raw information that gets used to evaluate a position. That's what beginner chess players use. Computers then use what are called piece square tables, which says how good is it to have a rook in this particular position on the board. And then they use much more complicated features still. You can look at conjunctions of different pieces in different positions. And if you look at recent shogi program, there's a shogi program I'm not going to talk about called Bonanza, and it's finally reached like human grandmaster level in a much more complicated variant of chess. And it uses something like 10 million different features, each of which is like some conjunction of different pieces in different positions. So you can make this feature vector very, very large, but the idea is just the same. I mean, it's exactly the same approach. So let's take an example of this. So let's look at Deep Blue. So Deep Blue, possibly still the most famous game playing program. So what did it do? Well, it had 8,000 handcrafted chess features, so the learning process was really done by humans there. So these features were learned by humans, and the weights were largely hand-tuned by human experts. So there was a team of human grandmasters figuring out, how good is it to have this particular pawn configuration in this position. But it did use this binary linear value function, and then combined that with a minimax search, which was a high-performance parallel alpha-beta search on these specialized chess processors, which back in, I guess this is 18 years ago now, it was already searching 200 million positions per second and was able to look ahead in some situations up to 40 moves into the future. So it was a very powerful search. So these minimax searches, when you combine them with all these extensions, can give a great degree of effectiveness. So the results, well, Deep Blue defeated Garry Kasparov, who was then the human world champion back in 1997. Although this was probably a premature victory for computers, because actually Garry Kasparov got a bit daunted by playing against a computer and made uncharacteristic blunders. There probably should have been another 4 or 5 years of research in computer chess before computers really were better than humans. But this has gone down in history as the moment where it really happened. It's absolutely the case now that the top computers are way better than the top humans. And this became the most watched event in internet history. So it was kind of a big deal when it happened. Okay, but no real learning, no reinforcement learning. This was a case of handcrafting combined with a systematic minimax search to compute this minimax value function with respect to a handcrafted value function. Okay, a second success story I want to talk about is a program called Chinook. So Chinook is a checkers playing program. It again used a binary linear value function. In this case, it had a much smaller number of features, which basically said how good is it. So checkers is the game of drafts. I'm sorry, I spent too much time in the US and Canada. So basically it has these 21 features that basically describe where the checkers are on the board and what configuration they're in. But it divides up the features into 4 different phases of the game. So you can essentially have different weights if you're in the opening or the middle game or the end game. And initially these were hand-tuned, but we'll see later how reinforcement learning was applied successfully to Chinook. And it actually outperformed the hand-tuned version, which was a nice result. But again, it used a high-performance alpha-beta search, and on top of that, it used this kind of backward search from the end game as well. So it searched backwards from one position, so it wasn't just a forward search from the root. It also searched backwards, where it basically said, if we know that this is a 1 position, let's back up 1 step and find all the places that we know can lead to a 1 position, and then back up from there again to find all the moves that can lead to a 1 position after 2 steps. And you can basically figure out then, by doing this retrograde analysis and backing up from 1 positions, you can consider all the simplified games with a small number of checkers, and you can play perfectly then from the last n checkers, where n, I think, goes up to about, in the latest results, I think about 11. So whenever Chinook got down to a situation with 11 or fewer checkers on the board, it was able to play perfectly without any search, without any, I just looked up in this table, what should I do, and it already had the result without doing any dynamic search. And so the results, well, there was this guy called Marion Tinsley, who was probably the greatest games player for any game in the history of games. He only lost 7 games in his entire career of playing checkers. So he played hundreds and hundreds of games, and he was just almost unbeatable. 2 of those games that he lost were against Chinook in a World Championship game to decide whether humans or computers ruled in the game of checkers. Unfortunately, the match was inconclusive because Tinsley had to withdraw for health reasons, and he actually died before they could have the rematch. And so this led Jonathan Schaefer, the maker of Chinook, to say, well, how can I really prove that, if we can't play against Tinsley anymore, how can we really prove that we could have beaten him? And he decided, well, the only way to do that would be to show that he could play perfectly against God. So he went on this mission and eventually solved checkers in 2007, and basically built such a large minimax search that it was able to search to the end of the game and figure out perfect play in this game. So it's not a small game. It has something like 10 to the, I think, 24 positions in the game. So this was a fairly substantial undertaking, but it was possible to solve checkers. It's not possible to solve larger games like chess, Go, and so forth. Okay, so that just gives you some background in search, and I think it's really important to have that background, because I think when we talk about machine learning and reinforcement learning, I think people have a tendency to forget the importance of search and planning, that there are domains, in particular these games domains, where search is the primary driver for achieving better performance. And I think it's very easy to go back into this mindset of, well, I'm just going to learn my value function and then I'm going to use it, or I'm going to learn my neural net and then I'm going to apply it, or I'm going to tune these weights and then I'm going to apply them. Whereas in practice, games in particular are an example where you really need to dynamically assess the situation and figure out, from this position here, what precise tactics should I follow to be in order to be able to achieve maximum performance. And so what we're going to look at is self-play reinforcement learning, but with a view to then combining this with search in the next section. Okay, so let's start by going back to our familiar methods for reinforcement learning and asking, can we just apply these in a self-play context now? And happily the answer is yes. There's almost no change necessary to take an RL algorithm and apply it in a self-play context. We just change the definition of the game to be self-play. There's now, we're playing for both players. So we estimate the outcome of the game. This return GT is just who won the game. And then all we do is, if we're doing Monte Carlo, well, we update our weights of our value function approximator. We update our weights a little bit in the direction of the error between who actually won the game and who we predicted would win the game. And then this tells us the gradient, how to adjust our function approximator to achieve that difference. If we're using TD0, then what we're going to do is we're going to consider the case with no intermediate rewards, where you just get 0 reward, 0 reward, 0 reward, and then you either win or lose the game at the end. So it looks a little bit simpler than our usual TD update. Well, we basically say, what we're going to do is, before I play the move, I can have some prediction of who's going to win, like I think black's going to win. But then I take a move and I figure out, actually now I'm in a situation where I think white's going to win. That generates a large TD error. So we say, actually I should have thought that white was winning all along. That's the error. We update the weights of our value function approximator, this estimator of the minimax values. We update that a little bit in the direction of the error between who I thought was going to win and who I then thought was going to win. And again, we have the gradient that tells us how to achieve that change. And we can do the same thing with TD lambda using the lambda return. So all our familiar machinery from previous reinforcement learning lectures is applicable in a self-play context. We're just trying to estimate these minimax values instead of the standard value function. And we're doing this in a setting where when we improve the policy, we improve the policy for both players. We don't just improve it for one player. We're trying to do this co-adaptation. So the policy improvement process becomes a policy improvement for both black and for white, so that we kind of get closer and closer to minimax, closer and closer to this Nash equilibrium. But functionally it's the same algorithm. You don't even need to change the code from what you would do in a single agent setting. Okay, So one thing which often is different is this idea of using after states. So we often are in the case in games where we have deterministic games with known rules, where we know the rules of the game, and what happens from my move has some deterministic successor. Like if I'm in some position and I play a particular action, there's some deterministic next state I'll end up in. Like if I play, move my knight in a particular way in chess, I know exactly what position I'll end up in. So in this case, we can define something called the after state, which is basically a way to think about the value of actions without having to explicitly reason about Q values. So what we can do is, instead of representing Q values, we can say, let's just look at the value, so that the optimal value, and we want to know which action is the best. And so to do that, we need to look at the action values. We need to say, well, if I'm in this position, should I move my knight here or my queen over here? Those are the different actions I can take. And so all we need to do is to look at the successor position that I would end up in if I actually took that action from that position. So I consider each of them separately. I look, let's take that move the knight over here, look at the position I end up in, we call that the after state, evaluate that after state, and now I just need to look at the after states of all the actions I could take and pick the one with the highest value. So we can do this because the game is deterministic and we have and we know the successor function. So we know the rules and we know what this will take us to. So we can very efficiently figure out what the best move to play is. And then the only thing we do which is slightly different is that instead of just maximizing when we do our policy improvement step, we maximize for white and we minimize for black. So this is just like in our minimax search tree, we want to maximize from one player's perspective but minimize from the other player's perspective. And so when we actually take our policy improvement step, all we do is we basically consider so from white's point of view, if white's going to play a move, we look at all the after states after all of white's moves that it's considering, and we pick the one with the best value. And from black's point of view, we look at all the moves that black could play, and we pick the one with the lowest value. And this is a way to improve the joint policy for both players. So this is a way for black to pull the score down, and for white to pull the score up. And if we keep doing this, this is the thing which, in principle, if you have the right algorithms, will converge on the minimax values by self-play alone. We don't need to build that big search tree. We just do our math. Okay. So let's look at some examples. Let's get into the details of when has this been successful. So I want to talk about perhaps two of the best known games where self-play has been successful, in Othello and in Backgammon. Backgammon example is particularly well known, but we'll start with Othello. So Othello is a game, probably most of you know it, but it's a game which looks something like this, and you have black and white counters, and what you have to do is place, if you kind of place, if black has placed a stone here, it would turn these two white counters, which are kind of caught, pincered in between those two black stones, would be flipped over to black. And so the game proceeds in this fashion, flipping over stones until at the end of the game you see who's got the most stones of the right colour. And so this is a very tactical game, but it turns out that it's possible to build a value function that performs quite well in this game. And the way that Logistello did this was to basically, instead of like in Deep Blue where all these features were handcrafted, what Logistello did was it basically discovered a large vector of binary features. So it built a binary feature vector containing 1.5 million features, and those features were basically configurations of stones which occurred commonly in the games it was playing by self-play. So if it was playing in all these games, you would kind of look at it and say, okay, let's consider, say, a configuration of 3 by 3 stones in the corner, and let's make a feature for each pattern that can occur in this 3 by 3 corner that actually occurs in real games. So there's a feature that kind of says, does this configuration of stones occur in this corner? If it does, the feature would have a value of 1. If it doesn't have a value of 0. And now we have a weight that basically says, how good is it to have a corner that looks like this? And you add together all of these different features. And basically what Logistello did was it discovered all of these different features within particular pattern constraints. So in Othello, the diagonals are particularly important. So it had features representing those diagonals, configurations of stones along those diagonals, along straight lines, and so forth. But it discovered which particular instances of those patterns it should have in its feature vector. And then it built a very large binary linear value function using these features. So it's got this giant feature vector that's discovered, and now it learns the weights for that feature vector by reinforcement learning. Okay, so this is all doing self-play reinforcement learning with feature discovery. And so what did the reinforcement learning look like? Well, it used a form of generalized policy iteration. So this is an idea that should be familiar to us all by now. What it did was it basically iterated over these phases. So first of all, it played itself a bunch of games. So it has its policies for black and for white, and then it plays itself a few thousand games, using search, by the way, to generate, using a minimax search to generate better play. We'll come to that in a minute. So it generated games of self-play using its current policy. Then it evaluated those policies, basically trying to establish the value function, like who's going to win under this policy? Is black or white going to win under these policies? Which is basically, you can think of as just a regression problem. It's trying to regress each position to who won in that position. So it kind of does this Monte Carlo learning, figures out, so I've got this batch of play, I start with my policies, I run these games of self-play, figure out who's going to win in these positions, and then improve the policy using that value function. So now improve the policy so that we look at the value function and white picks moves that maximize that value function and black picks moves that minimize that value function to generate two new players for black and white. And then iterate and repeat this process again and again and again. And so the results were very effective, that just from self-play, no prior knowledge apart from this minimal little piece of prior knowledge about what regions of the board should be considered for features, it was able to go off and beat the human world champion Takeshi Murakami 6-0. So it was actually the first program to achieve superhuman performance in any one of these classic games. Okay, so that's Logistella. Is this roughly clear? The only part I've skipped over is search, which I want to come back to in a minute. So I don't want to give the impression that search was not necessary in Logistella, because it used a minimax search in every position. Whenever it actually played a move, it basically did a big minimax search using the value function which it's learned here to pick the next move. So really the generalized policy improvement is a policy improvement not just based on a one-step max, but on building a large minimax tree using the current value function. That's how it improved the policy. And this was crucial step. Okay. I now want to talk about TD Gammon, which is still, like almost 20 years on, the most famous application of reinforcement learning by Jerry Tesaro, who was at IBM Research. And so it's applied to the game of backgammon. So don't really need to talk about the rules, but roughly speaking, backgammon has a board which looks like this, with all of these different checkers, for, let's call them black and white, just to be consistent. And the idea is that one player is trying to get all their checkers to move around in one direction, and while the other player is trying to get all their checkers to move around in the other one. And if you roll dice to see where you move your checkers to, and if you land on top of someone else's counters, then they're sent back to the beginning again. So it's like a race to see who can get to the end, but it's a race where there's actually interactions between the players. It's a real game. And what TD Gammon does is it basically has this nice representation of the board. It basically takes the board and it flattens out this board into this state vector here that basically says for each of these locations on the board, how many checkers are there in that location. And it actually has, I think, 6 features for each location, saying, is there like one checker here? Is there one white checker here? 2 white checkers here? Are there 3 white checkers here? Is there 1 black checker here? 2 black checkers here? And so forth. So it's got a separate feature for each possible count of stones at each location on the board. And that's the binary feature vector that it uses as an input. What's different about TD Gammon from, I think, any of the other examples we're going to talk about today is that it used a nonlinear function approximator. It used a neural network. And it basically used that binary feature vector as the input to a neural network. The number of nodes in this neural network diagram are not accurate. It used something like, I think, 40 or 80 hidden nodes, and it was, a long time ago you couldn't build big neural networks. And it built a neural network with just one hidden layer, output a value function saying, if you feed in some description of some position here, it will tell you who's going to win the game? You know, what's the probability that black or white will win this game? That's the value function there, the expected outcome at the end of the game. So that was the idea in TD Gammon. It used this nonlinear value function approximation, and then it applied reinforcement learning. So famously, TD Gammon learned just by self-play alone, again, self-play reinforcement learning. It was basically this neural network was initialized completely with random weights. It was trained completely by games of self-play, and it used a very simple update, which was essentially the temporal difference learning algorithm we were just looking at. So it actually used TD lambda, but you know, this is the TD0 update, where we just compute the TD error. It's just what we saw earlier, the difference between what I thought was going to happen in this position and